All right, we're studying charge, and this is the beginning of the new unit. And we need to introduce exactly where charge comes from. But charge is a fundamental unit of matter. There are other fundamental units, fundamental properties of matter that we've talked about before. Okay, we talked about mass. Okay, in fact, it's not really just about matter. It's fundamental property of, or fundamental unit in the universe. There's mass. There's length. There's time. Okay, and these are the ones that we've dealt with so far: mass, length, and time for all of our previous units. So for momentum is mass times the length divided by time, and energy is a mass times the length squared divided by a time squared, and all these, we have all these other units. We're introducing a new one, and the new one is charge. And we get charge charge comes from primarily electrons. Charge comes from electrons, which brings us to, well, what's an electron? And most of you guys are, I think, have a basic idea of what an electron is, but I want to make sure that we have the right concept about it. So, all matter in the universe, okay, or most matter in the universe, it's not a subatomic particle, is made of atoms. And in the center of an atom, we have two different kinds of particles. Okay. In the center of the atom, we have this thing called a nucleus. Okay. The nucleus contains two parts to it. It has protons, and it has neutrons. Okay. The purposes of these we don't necessarily need to get into, except I do need you guys to know that a proton will have this symbol, okay, a P with a little plus above it, and that plus means that a proton has a positive charge. Okay, it is the basic unit, it is the simplest amount of charge that we have for the matter that we deal with right now. Is a plus, it has a +1 charge. Neutrons have a 0 charge. Okay, and I tend to color code things, so my protons are going to be red. My neutrons will be blue. Okay. And then around the nucleus, we have, and they're not in circles like sometimes you see, or like you see in my logo, what I've got the little zoomies around it. That's not really what they look like. They exist in regions of space called orbitals, but again, that's also not real pertinent to what we're going to study. But these are the balance to the positive charges that we have in the nucleus. These have a negative charge, and these are the electrons. Okay, and around the nucleus we have electrons. That is E minus, and I'll draw those green. Now, if this is a normal atom, we're going to have a balanced amount of charge on this thing. And so we have, how many reds did I draw here? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is going to have This is going to have 14 electrons around it, and they're There is a pattern to how they're distributed, but again, that's not our worry right now. Okay. The idea, however, is in any particular atom, the protons stick around. They stay there. This is what defines the property of the atom, is the amount of protons. And all of the positive charge that we see in an atom stays in the nucleus of the atom. The electrons, however, are very, they're volatile, and they are movable, and they're constantly moving, they're constantly popping around, and they don't necessarily have to stay around the nucleus of the atom. They're free to move to other places. Okay. And this negative charge, this is the fundamental, the minimum charge that an object can have. All right, if there are, okay, and I want you to put this number down because this is a new number that you guys are going to need to memorize, and it's a big one, unfortunately. Okay, it's this. The charge on an electron is 1.6 times 10 to the negative 19th coulombs. Coulombs. C-O-U-L-O-M-B is a Coulomb. Okay, it's a French dude. Okay, so this is how our charge exists today. But this isn't how we dealt with it to begin with. In the beginning of our study of electricity, we found out what this unit of a Coulomb was. Okay, we defined this basic unit of a Coulomb as it was sort of an arbitrary amount. And it is from this unit of a Coulomb that we're going to see other units come out. And we're going to be dealing with things in terms of coulombs. Okay, 1 Coulomb will lead to things like volts, okay, and ohms. You guys may have heard of those, and amps, or amperes, for a unit of current. Okay, all of these are based on our unit of a Coulomb. These were all determined long before the start of the 20th century, okay, the early 1900s, which was when we discovered what an electron was. And so there's a little bit of story here. Okay, Ben Franklin. Yes, that Ben Franklin. Okay, is one of the pioneers of the study of electricity and magnetism. And that's not, there aren't too many people that really realize, they know Ben Franklin. He's one of the guys that signed the Declaration of Independence. He's a founding father, that sort of thing. He was quite possibly the colony's foremost scientist and inventor. This guy was something else aside from the fact that he was involved in our politics. Ben Franklin studied currents. And he knew that current flowed through a wire, that it went from one place to another. And this is something that he was able to study. And if we cut the wire, if we broke off the wire, found a way to disconnect it, then current would stop. And if we attach it, then current would flow. And he arbitrarily determined that when something was flat on his table, if something would go clockwise, based on how he hooked up his power source, that this would be the positive direction. Well, we find out later that what's actually happening is, if this being the positive direction, what's actually happening is that we have electrons which have a negative charge are actually going in the opposite direction. And current, a positive direction for the current is actually the negative flow of electrons. It's the negative direction. Electrons flow the other direction. You follow? And that is how this electron became this negative charge. Okay, in fact, if Ben Franklin had just selected the other direction to be positive, electrons would be positive, protons would be negative, and all of our electricity and magnetism study would be flipped in terms of charges. So it's kind of an interesting serendipity there. Okay, so from this, we're going to introduce Coulomb's law. Here's Coulomb's law. Electric charges exert forces on each other just because of their charge. And you guys have seen this before. This is the opposites attract. This is the opposites attract, likes, repel thing. And so the force of electricity, okay, between two charged objects is equal to K, and I'll explain what K is here in a minute, times the charge of the first one. And the way we write our variable for charge is Q. So we have the charge on one object times the charge on a second object divided by the distance between them squared. You might have seen this before. Does this look familiar? Yeah, Q is charge. Okay, so K is the K equals 9 times 10 to the 9th Newton meter squared per Coulomb squared. Q is charge. Charge in coulombs. And R is the distance okay. R is the separation of the charges. That's what those letters. And so whenever we have Q, whenever we write this little Q, that means our charge, and that's going to be our coulombs. And essentially, it is a way of counting how many electrons, how many more electrons we have than protons, or how many less electrons we have than protons. So if we have more electrons than protons, what, in general, what's our charge going to be? If we just have more electrons than protons, it's going to be negative, right? And if we have fewer electrons than protons, then the charge would be positive, right? So we very rarely have an object that is entirely positive, that is just made out of protons and with some neutrons in there, that has no electrons. Very rarely does that happen. And vice versa, we occasionally have just electrons, and you guys will see that. I'll see if I can demo some electrons here later on today. Okay, this law is just like Newton's law of universal gravitation. You guys have seen this before. Force of gravity equals G m1 m2 over r squared. Does this look familiar to you guys? Okay. Look at the similarities here. They're almost exactly the same. Okay, in fact, the equations are exactly the same, except we're just doing it with a different constant and different variables. Okay, so we're going to take a look at this here for a sec. Opposites attract, like charges repel. If Q1 and Q2 are opposite charges, that means we're going to have a positive times a negative, or a negative times a positive, right? That makes sense? Mm-hmm. If you guys multiply a negative times a positive, what do you get? Negative. You get a negative, right? Okay, so if this force Okay, if our electrical force is negative, that means they attract. Okay, and that means that they're moving towards each other if the force is negative. If the force is positive, okay, which we would get a positive times a positive gives us a positive, right? But so does what? Oh. If we have a positive times a positive, we get a positive. But how else can we do it? Negative times a negative will also give us a positive. And so if our electrical force is positive, then they repel. All right, so this is, if we have opposite charges, they attract. And if they have like charges, they repel. And that's how Coulomb's law works. That's really the basis behind electric charge. And that's where we're going to stop for today.